Today we're going to be taking notes on 4.3 wave characteristics. A wavefront is an imaginary line on a wave that highlights the part of the wave that is moving together or is in phase. The wavefront is also perpendicular to the direction of the ray, and the distance between the two waves is one wavelength. A ray is just the line that is showing the direction that the wave and the energy is traveling. Let me show you an example. There's a vibrating wooden bar, and this is consistently put into the water and out of the water, touching the water's surface at a consistent rate. This produces waves, and these disturbances are seen traveling from left to right. The direction of the energy is moving from left to right, and these lines over here are specifying the rays. It is the direction that the wave and the energy is traveling. Wavefronts are lines or surfaces that join all the crests or points vibrating at the same phase. If we were to connect all of the crests, we would get these lines here. And these lines are the plane wavefront. So this is an imaginary line that shows all the particles that are moving at the same phase. These are also lines that are perpendicular to that of the rays. Notice that the plane wavefronts are also equal distances apart, and that the distance between two successive crests is called the wavelength. Wavefronts can also be circular. By touching the water surface with a dipper, as seen here, the circular waves can be seen moving outward from the center and the source of the disturbance. So, as the dipper is put into the water, a small wavefront is produced that then emanates out and becomes a larger circle and a larger circle and a larger circle. We can see that the rays are pointing in this direction, and this is all in all directions away from the source of the disturbance. These are called the rays. The wavefronts are the black concentric circles joining all of the crests or the points that are all in phase, and notice that they are the same distance from the source of the waves. Wavefronts are perpendicular to the rays here, just as they were with the plane wavefronts. The wavelength is again the same. It is from wavefront to wavefront. So as you can see, understanding wavefronts and ray diagrams can help us to illustrate how waves behave during different situations, such as when there is reflection, refraction, or diffraction. We will be learning about reflection, refraction, and diffraction in more detail in the next section, but I just wanted to let you see how useful wavefronts and rays can be when you're trying to illustrate how waves behave. In this first picture here, you see that a wave is moving towards a barrier. At the point of collision, the wavefront changes at an angle of incidence, and that angle of incidence is equal to that of the angle of reflection. Here the green lines represent the rays, and the blue lines represent the wavefronts. And notice that this one wave changes the direction and the angles at which the wave is traveling. Notice also that the wavelength stays the same because the medium the wave is traveling through is the same. In the next example, we are noticing a wave undergoing refraction. In this case, the wave does not encounter a barrier, but a difference in the medium that it is traveling through. One thing we know is that the speed of a wave can change depending on the medium. In this example, a wave is traveling through at a certain speed. When it enters into shallow water, the wave slows down and bends because the water is more dense. So what you're seeing here is that the wavelength decreases, and this is in order to conserve energy because the speed decreases. The frequency is the same, so conservation of energy is upheld. In the third example, there is diffraction. Here you actually see a laser that is emitting a disturbance, and that these disturbances are heading out towards this barrier, and here we see the wavefronts and those are denoted by the red lines. And the black line that is heading straight into the slit is the ray, which is perpendicular to that of the wavefront. When the wave reaches the barrier, most of the waves will hit the barrier. There's a small amount of the waves that do make it through the slit. Here the waves spread out, creating circle wavefronts, and the rays are also shown as being perpendicular to that of the wavefront. Notice that the wavelengths have not changed before and after having passed through the slit. We know that amplitude can change. A higher amplitude is perceived as a sound that is louder. A lower amplitude is perceived as a softer sound. In terms of sight, we perceive colors as being brighter when the amplitude is higher. And when that amplitude is lower, we perceive the color to be less bright, to be dull. We call this increase or decrease in amplitude the intensity of a wave. A higher amplitude has more energy, therefore it has more intensity. A wave that is lower in energy has a lower amplitude, and also we can say that it has less intensity. Wave intensity is defined as the amount of energy per unit time flowing through a given unit area. This is normally measured in watts per meter squared. Looking at this picture over here, which you do not have to draw, you see light filtering out onto the lawn. Imagine a window that has an area of 1 meter squared. If 1 joule of light energy flows through that window every second, we can say that the intensity of that light is 1 watt per meter squared. And that is given that we know that a joule per second is equivalent to that of a watt. There is a relationship between intensity and amplitude. We know that to be intensity is proportional to the square of the amplitude. If you double the amplitude, you increase the wave's intensity and its energy by a factor of 4. The relationship between energy and amplitude is that energy is directly proportional to the square of a squared. Looks very similar to intensity being also directly proportional to the square of amplitude. This is because as intensity increases, the energy in the system also increases, which is directly linked to that of the amplitude. A high amplitude means a higher energy wave. A low amplitude means a low energy wave. This is very important for people who like to surf because they're always looking for a specific height of a wave in order to know the intensity and amount of energy that wave has. How is it possible that energy transported is related to the amplitude? Let's look at this pendulum where there is a certain amount of displacement. Here we have the maximum displacement being at this height. The displacement is due to the force that is applied to the bob, and it allows the bob to be displaced a certain amount from the fixed point. If you were to pull the bob further away from the fixed point, you would be adding more energy into the system, which creates a larger displacement. And from a pendulum swinging, we know this to be simple harmonic motion, we would be creating a higher amplitude. This shows the relationship between energy and amplitude. Because the amount of energy is different depending on where you are on the wave, for example, if the surfer is here versus a little bit lower along the wave, it makes sense to talk about energy per time, or power. Remember that power is energy divided by time. Because energy is dependent on the square of the amplitude, so is power. Because the energy changes with time, for example, a wave that is heading in toward, because the energy changes with time, for example, a wave that is heading in towards a beach, it is good to discuss the power that is spread over some amount of area. For example, here we have water coming in. We have the waves with a certain amplitude. Let's say that there's an object in the path of the wave, such as this house right here. Most of the wave's power will not contact the object. Only this part that touches the the house will transfer that energy. So instead of talking about the total energy of the entire wave, we can actually find out the energy or the power that strikes that object. We want to know the power per area to find the amount of power that is delivered. This is called intensity. Sometimes light comes out from a point source. When a wave, light for example, originates from a point source, the intensity falls off or decreases by 1 divided by r squared. In our data booklet, you see this as intensity being directly proportional to x to the negative 2. X is the same as being r, which is the distance from the center. Let me try to explain how this is true. Let's look at a point source where a spherical wavefront is coming out in all directions. So of course you're going to have to imagine that this is coming out in all directions, even towards us and away from us. This is just showing it very flat. The total amount of energy delivered from the source, for example, let's say if this was the sun, the amount of energy would be fixed. This disturbance would then emanate out in all directions. In a sphere, the amount of energy emitted and is found at any point along that wavefront is going to be the same. So the energy along this wavefront will be the same. The energy along this wavefront will also be the same. Let's say that this wavefront here moves out and is located now here. The area has increased by the surface area of that sphere. So what we have is that intensity is equal to some constant power, which we will say is P, and it is divided by the amount of area for a sphere. And we know that a sphere's area is 4 pi r squared. So pretty much the power, the 4 pi, are going to be a constant. The radius, however, will continuously be changing. As the energy continues to move further away from the point source, there will be larger spheres of area. The intensity then would be spread out over a larger area. So the intensity will decrease by 1 divided by r squared, because this is the only variable that is changing. As radius increases, the denominator becomes larger and the intensity will decrease. Here's a picture where it actually shows that as you move further away from the point source, the intensity would decrease because the amount of energy or the amount of power would be spread over the amount of area that is shown here. The amount of area would increase that the power is dispersed across, so therefore the intensity would decrease. And this also helps to explain why intensity is directly proportional to that of x to the negative 2, which was seen in the last slide.